Hi there and welcome to the WhistleBig Classroom. Today we're going to talk about Glider 101, or how do gliders glide. If you ever looked at an airplane, you probably noticed that it has an engine. Most airplanes do. We have a jet engine or a propeller or sometimes even a rocket. But a glider is the simplest of all airplanes, and it doesn't have any of those things. It doesn't have a rocket, it doesn't have a jet engine, it doesn't have a propeller. And yet they manage to fly quite well. So we're going to talk about how they do this. Now the first thing to look at in any airplane is lift. All airplanes must have lift, otherwise they just fall to the ground. And to make lift, we need two things. We need airspeed, which is the motion of the airplane through the air, not over the ground, but through the air. And we need something called the angle of attack. Now what is the angle of attack? Well, the angle of attack is the difference between where an airplane is pointing and where an airplane is going. So if this airplane is going this way, horizontally, perfectly level, but pointing this way, the angle of attack is this angle here, which we call alpha for short. And the lift is always perpendicular to the direction the airplane is traveling. So we can draw a lift vector pointing straight up because the airplane's flying horizontally, and that's our lift. And the other thing that we have, as a consequence of lift, is that we always have drag. Drag always points against the direction of travel. Okay, so we've learned a lot of things, but we did leave one thing off here. One is weight. We said we needed lift to oppose weight, so let's put that on here and let's draw these to be the same length. You'll see why in a moment. Alright, so what do we know now that we've established what the forces are on our airplane? Well, we can apply Newton's second law of motion. Sum of the forces on the airplane is equal to the mass times the acceleration of the airplane. Well, what are the sum of the forces? Let's look at the up and down forces first. And any force that's up, we're going to call positive. So there's lift, and then we have weight, which is downwards, and there aren't any others. It's equal to ma. Okay, well, what do we know about this picture? We know that the airplane is traveling in a straight line this way. That means that it doesn't have any velocity up, and it doesn't have any velocity down. And it also means that the velocity is not changing. It's zero and it's staying zero. That means that the acceleration in this direction is equal to zero. Well, we know the mass of the airplane can't be zero because it's an airplane. So all that's left is that the acceleration must be zero. And if that's true, lift minus weight equals zero. Move the weight over, lift equals weight. So in straight and level flight like this, we are able to show that lift is equal to weight. Likewise, if we knew that lift was equal to weight, we could show that the acceleration in the vertical direction was zero. But what about drag? Okay, well, drag goes this way. Let's write down everything that's going this way. So drag to the left, we're going to call negative plus nothing. There are no forces going in this direction. The airplane only has drag on it. Well, what does that tell us? That tells us that the acceleration of this airplane, and if we move this over here, drag divided by mass is equal to acceleration, that the acceleration is negative, so the airplane's going to slow down because that's negative, as we said, was that way, and it's not zero, so the airplane must slow down. Okay, well, what does that mean? We said that the airplane needed to have airspeed to make lift. And in fact, lift is very dependent on airspeed. If you double the airspeed, then you get 4 times the lift. So even losing a little bit of airspeed is going to cause the airplane to slow down a lot. If it does that, it's going to start to fall because lift won't be equal to weight anymore. Lift, if this gets smaller, lift gets smaller, and the airplane will start to fall. And if the airplane starts to fall, then the velocity starts to increase in this direction, and that makes the airplane fly downwards. Interestingly, stable airplanes, no matter which way they're pointing, will always maintain the same angle of attack. We'll talk more about that in another video, but this is something that we just need to keep in mind is true. So the airplane's going to start to fall. It won't pick up speed forever, and that's another topic, but it will end up with its velocity vector pointed like that. And we said the angle of attack was going to remain the same, so we'll draw the center line of the airplane. And we'll draw kind of a messy airplane here. And this is the direction the airplane's pointing. This way is level, just so we have a reference line, and here's our angle of attack. Okay, so that's what it's doing now. It started to fall, it found a new direction to go, and it's falling this way. What happens? Well, the lift, we said, was perpendicular to this, and the drag is parallel to it. That looks a little bit different. We can actually look a little more closely at this lift vector, and the vector just means something with a direction. So let's look at this lift in detail. We can see that some of the lift is pointing up, and some of the lift is pointing forwards. Also, the drag vector, some of the drag is pointing up, and some of the drag is pointing backwards. And of course, we still have our weight. Didn't draw that in a great spot, but the weight hasn't changed. It's still pointing downwards. Just have to make that a little shorter because I ran out of room there. In fact, we'll just draw the weight right here. Because, since we said this is no longer changing direction, that means that whatever speed this is, isn't changing anymore. So it's not accelerating. And whatever speed this is, isn't changing anymore, so it's not accelerating. So that means that the airplane, again, has zero acceleration in the up and down direction. So we can write the lift up plus, we now have this thing, the drag up, minus weight is equal to ma, but because there's no acceleration, that's equal to 0. We can also write the lift forwards minus the drag backwards is equal to ma, and that's also equal to 0, or because this velocity vector is not changing anymore. And so what's happened is, because the airplane started to fall and found a way to slide down this ramp of air, it's arranged the lift so that the lift upwards plus the drag upwards is equal to weight instead of just the lift. But the lift forwards now is equal to the drag backwards. And that allows the airplane to remain at a constant speed. Now, of course, there's another way we could have done this. If we'd put a propeller on here and produce some thrust, then the airplane could fly perfectly level. And that's why when you fly a glider, you will notice that in still air, it will always glide downhill. It won't stay in level flight for very long because it'll immediately start to slow down and it will find itself heading downhill. And the only ways to make it to stay up in the air are either to put power on it or to cheat a little bit and find some lift. And we'll talk about that. When we say lift, we mean a thermal or some other kind of rising air. We'll talk about that in another video. But that's how gliders work. They simply slide down this ramp of air and arrange the lift to put all of the forces into equilibrium so that the sum of the forces upwards and left to right are equal to 0. Well, we hope you've enjoyed this. We hope you learned something, and we hope you come back and see us again soon. Until then, take care, and bye-bye.